Yeah, so my horrible scale-up story of doom, as I said, is late summer, early fall of 2006. And in the Gelman group, we, as you saw some of the stuff last week, we used cyclic beta amino acids to induce short peptides to form helices. And there was this one beta amino acid, which we called ACPC. It was a 5-membered ring instead of a 6-membered ring. And interestingly enough, the 5-membered ring amino acid had slightly different properties from the 6-membered ring amino acid and preferred a different kind of helix, different kind of hydrogen bonding pattern. Kind of cool. But the goal was to make this, and you had to start with the following beta keto ester. Yeah. I'm not showing stereochemistry because it didn't matter. That stereo center was going to go away anyway. And we'd use acetic acid and an expensive chirolamine. This is seared into my consciousness because I can still remember how, and I don't remember what enantiomer it was, but you would first make the imine, which would spontaneously convert into the enamine because of the acidity of the alpha proton. And this is the chiral, enamine. Then you do, and the 2-step reaction series was reductive amination. You would use sodium cyanoborohydride, which is a form of borohydride that you can, anyway, I can't remember. No, it's got to be 3. Yep. That you can use in protic solvent, and that would reduce the enamine to the beta amino ester with the appropriate stereochemistry, or at least you would get the desired diastereomer as the major product, and then you could separate it from the other diastereomers. And then after this stage, you removed the amino group by hydrogenolysis, you saponified the ester, and then you protected with FMOC. So, well worked out chemistry, not that hard. And I had done the reaction before, but we were always running out of this. And so I thought, I'll just do it on large scale. And the reason I did this is because my friend Justin had, in his recent past, made an enormous large-scale synthesis of the 6-membered ring derivative in sufficient amounts that he was able to get done his thesis work and get on with his life. But I thought I could do as good a job as Justin did. I was wrong. So I set up this first reaction and poured in, I mean, the scale, it was like a 25-liter flask, so large. I poured in these 2 reagents by the bottle, and the chirolamine is kind of expensive. And so you're supposed to reflux them, and I was going to reflux overnight to get to the enamine, and then the next day add the sodium cyanoborohydride to get this, and then I would carry it on. I made a critical error because with that kind of flask, the only way to heat it is with a heating mantle. And so I turned on the heat, put on a condenser of some sort, and then left. And overnight, it refluxed out through the condenser and oozed outside down my hood and all over the floor, and it was sticky and smelly, and I got a call at like 10 o'clock at night. Your reaction is all over the place. So I came in and I cleaned it and fixed it up. My advisor wasn't there and didn't know, but in the Gelman group, you always confess your sins, and then there's a obligatory cautionary tale in group meeting that you have to give. And I learned my lesson, which was if you're going to scale up, make sure you can be there to watch it so that it doesn't destroy itself. Anyway, highly embarrassing, and I still haven't gotten over it, and it's been 14 years. So, but now you know to be wise. Scaling up is tough. Okay. It still embarrasses me. I'm like, gosh, now these kids think I'm an idiot.
And you just make us feel better because you do dumb things too.
Yeah, so if you let the HPLC overflow and you get acetonitrile over the floor, done that before. What else is stupid? Break glassware, definitely done that before. Put something on the lyophilizer in a way that somehow makes the lyophilizer lose vacuum and causes other people's samples to melt. Done that before. Cracked CD cuvettes by running them at high temperature with the cap on. Done that many times. So anyway, lots of mistakes. But I'm not the one responsible for the solvent system fiascos that Dr. Castle keeps sending emails about. That was not me. All right. I just wanted to show you, last time we were talking about cation-pi interactions, and I wanted to show you a few electrostatic potential diagrams. I know we were searching the internet for some and couldn't find them. I just went and did the calculations myself to generate these electrostatic potential diagrams. So remember, the numbers on the bottom of this panel refer to binding energy of sodium for these various arenes. And I just wanted to demonstrate that the energy of binding really does correlate with how electron-rich the face of the ring is. And in terms of this observation that phenol isn't any different than benzene, you may have remembered from 351 or 352 from sophomore organic in any case that phenol is an activated molecule relative to benzene in electrophilic aromatic substitutions, which is true, so you may have been surprised that phenol doesn't bind sodium any better than benzene does until you compare their electrostatic potential surfaces and see that in terms of the ring it's about the same. Which suggests that at least for phenol, the resonance donation effect is sort of balanced off by the inductive electron withdrawal effect due to oxygen's electronegativity. But that resonance effect dominates once you get to the high energy carbocation intermediate of electrophilic aromatic substitution. For aniline, the nitrogen's also electronegative, but you can see clearly the aniline is way more electron rich because of the intense red color in the ring. And it does bind sodium with a lot more affinity than did benzene, and that correlates with the difference in color. You put electron withdrawing groups and the affinity goes down. Here's fluorobenzene, and now the interior is not quite red, and it's not even yellow. It's sort of this pale, sickly green. I tried to do the cyanobenzene, but I run out of time. So in general, Doherty believes that if you want to get a sense for how strong various cation-pi interactions are going to be, just make the electrostatic potential surfaces, and it tracks pretty well with that. Okay. A couple other things that pi systems can do. Just as we've talked about how the faces of arenes are electron rich, the edges tend to be electron poor. And so occasionally in proteins, you're going to see what people call AnionPi interactions. And it seems kind of a little bit deceptive because actually the pi system of the ring isn't involved. It's just an interaction with an anion, between an anion and the electron poor edge of a ring. So if we're looking at a ring on a benzene ring on the side, you might imagine that, and I forget what color we're using for electron poor. I guess we'll use blue. It's possible and reasonable, and you find in a lot of cases anionic amino acid side chains in the vicinity of the edge of an aromatic ring. And that interaction can be worth in the 0 to 3 kilocalorie per mole, and that's sort of par for a lot of these non-covalent interactions. We measured, well, we thought we measured the affinity of an AnionPi interaction in my lab. The situation was a little complicated because we didn't have structural data. And I'll just show you a couple of the figures. If you're sick of hearing about my research, so am I. So, nope, not that one. All right, so we had a reverse turn, a loop in a protein called the WW domain, which is just our playground for non-covalent interactions. It's a protein we understand really well, and you can measure its folding really easily. And within this loop are two residues that are fairly close to each other. And we knew that both of these positions were fairly loose with respect to substitution, so you could put different things here and here without destroying the ring. At position 16, we put either the wild type amino acid serine or a negatively charged residue. At position 18, we put either the neutral asparagine or an aromatic residue. And so by putting either serine or aspartate here and either the arine or asparagine here, we could subtract away the effects of the individual substitutions and figure out if there's any synergy or favorable interaction between any of these arines and the aspartate. And what we found, let's see, sure, is this lovely table of data. The important things I'll just highlight. You can, oh, that's far too large to highlight. You can observe an interaction between tyrosine and the negatively charged amino acid. But interestingly, that interaction is a lot better for phenylalanine. And we wondered what the nature of this interaction was. Ideally, you would think, based on what we've just talked about, that the negative charge would have to be interacting with the edge of the ring. And so we thought, what if we switch the electron density of the ring such that the edge of the ring is now electron rich? Would you then see this stabilizing effect go away? So we made the pentafluorophenylalanine derivative and figured that putting the negative charge here would then be repulsive, and that would be bad. It turns out that if you put the pentafluorophenylalanine there, actually the effect stays the same. But fear not, we don't think all is lost, because if it's possible for this ring to rotate, and this is where structural data would be nice, if the ring can rotate a little bit, then maybe what you actually have is a face-wise AnionPi interaction, which is totally allowed because in a pentafluorinated, I realize I changed who had the, dang it. In a fluorinated benzene ring, the quadrupole is reversed. Now it's the face that's electron poor and the edge that's wait, did I say that right? Yes, now it's the face that's electron poor and the edge that's electron rich. And so we think that this turn is, this loop in the WW domain is flexible enough to allow, dang it, edge to face and edge to anion and face to anion geometries. One interesting observation, though, is that the aromaticity is absolutely essential. If you replace the aromatic ring with a 6-membered ring cyclohexane, the effect goes away. So whatever we're observing, it does depend on the quadrupolar nature of the benzene ring. Benzene rings are also known to engage in what your text calls PolarPi Interaction. Some people call these XH-pi hydrogen bonds. And just sort of by analogy to hydrogen bonds. An example of this is just, that's not a triple bond, that's a single bond. You could imagine ammonia directing its electron-poor hydrogens toward the benzene ring. In the gas phase, this is worth about 1.4 kilocalories per mole, so much weaker than the cation pi interactions, which are worth 20-ish kilocalories per mole in the gas phase. We've started to study this kind of interaction in my group because in our favorite playground for non-covalent interactions, we observe a situation where we have an amide bond directed right at the space above an aromatic ring. This is the indole ring of a tryptophan side chain. And we're currently working on trying to understand whether that interaction is worth anything. And my student, Steve Draper, is doing some of that work. In parallel, I've done a calculation on a simplified system. This is benzene and acetamide optimized geometry. And you sort of have this amide proton pointing down towards this side of the ring. And at least as I measure it with DFT calculations in the following basis set, it's worth about 5.6 kilocalories per mole in the gas phase. So we're working on understanding that. Specifically what Stephen did is he attached a PEG polymer here, and the protein got more stable, and he thinks it's because PEG is protecting that interaction. Okay. Questions about non-covalent interactions? I don't have much to say about the induced dipole type interactions, other than that their distance dependence is really, really tight. So induced dipole interactions, that's or London dispersion forces or van der Waals interactions, those fall off with 1 over r to the 6th. So that's a much, much more sharp distance dependence than you see for full-on charge interactions or even for dipole interactions. All right. Now I want to talk about the hydrophobic effect. I'm leaving out a new sort of favorite non-covalent interaction. I'm just going to mention it briefly. You can go look it up if you're interested. These are called N to pi star interactions, and they've been studied a lot by people like Ron Rains and Neil Zondlo. And it's kind of an unusual interaction that probably has been important for a long time, but its importance has only recently been appreciated. So let's talk about the hydrophobic effect. What do you know about the hydrophobic effect? Go ahead. Yeah, Austin. Entropy driven? What do you mean by that?
It's not the hydrophobic molecules
Okay. Good. What else? Yeah.
Important for proteins to have their curved shape.
Okay. Key for proteins. I can't spell or write, but that's all right. Key for protein folding. Yep. Oh, why can't I have to click insert photo and then we're good. All right. So here's an image from your text. And it shows a network of water molecules around some nonpolar things. And then it shows that same network of water molecules when the nonpolar things are together. In your book, it talked about how making and we talked about this when we were dealing with solvation, that dissolving something in water involves first making a cavity for that thing to be in. Do you remember what happens to water when you make the cavity? Okay, more local ordering because there's space that you can no longer occupy, so degrees of freedom are definitely reduced. Okay, what else? How about the water molecules on the surface of the cavity? Their freedom is reduced. Go ahead.
They're forced into a certain arrangement by the thing they're surrounding.
Forced into a certain arrangement by the thing they're surrounding. What do you suppose happens to their hydrogen bonds? They might lose options, and so because they don't have the freedom to be in every which way, and there's this whole area in the middle where they can't, where hydrogen bond partners are not available, so the remaining hydrogen bonds get stronger. Okay, so they lose some hydrogen bonding ability, but the hydrogen bonds that remain get stronger, and the freedom, the flexibility, and the ability to move around of the molecules in the immediate vicinity of that cavity is lower. Okay. So when you combine cavities, you can fit these two molecules together in a cavity that's probably smaller than the surface areas of the cavities previous. I don't know if that makes any sense at all. Think about whatever sphere envelops these nonpolar molecules, and think about if we could measure the surface area of those spheres. Then do the same thing over here. Probably the surface area here is smaller than the sum of the surface areas before. Okay? So that means there are water molecules that used to be part of the area around the surface that are no longer there. They used to have lower entropy, and they used to have fewer H bonding partners. Now they have lots of freedom, and they have more H bonding partners. And so overall, you've dramatically increased enthalpy. In terms of what you've done to entropy, you've dramatically increased entropy. In terms of what you've done to enthalpy, it's a little bit more confusing because you have to account for the reduced hydrogen bonding that came from putting these nonpolar solutes in water to begin with, and then the fact that the hydrogen bonds that surround the cavity are stronger as a result of the fact that there are fewer of them, and then the better hydrogen bonding you get when you release water molecules to the bulk solvent. So the enthalpy effect is a little bit complicated, but you're right, overall, what you observe in this process is an entropically driven effect. Okay? So why isn't this an issue for polar molecules or for salts? Go ahead.
The water can form new interactions with them that pay for the breaking of the solution.
Okay, good. So if you have a polar molecule in this cavity, you don't lose as many hydrogen bonds because the thing can hydrogen bond with water. And at that point, everybody's entropy is fine because you got options, right? The water can hydrogen bond with the solute or with itself. There's the interactions that you form pay for the interactions that you lose. So a key hallmark, couple of ways we can interpret this diagram. If we go from left to right, this is like dissolving a crayon in water, or dissolving benzene in water as an example, or vegetable oil in water. Not favorable, right? Or going in this direction, that could be protein folding. Protein folding happens because you have a long backbone, a long chain, and along that backbone you have some non-polar amino acids which experience the same thing as hydrocarbons. And then you also have polar and charged amino acids on the other side. And the protein will tend to fold. Prior to folding, you have the network of rigid water molecules surrounding these non-polar side chains, unable to interact with them and with reduced degrees of freedom. When you fold the protein up into its three-dimensional shape and many of the non-polar side chains are inside, suddenly those molecules which used to be, I don't know, that's dumb. Suddenly the water molecules that used to be bound around the surface of the non-polar groups are now free to lots of degrees of freedom. So it's important to think about the hydrophobic effect in both sort of directions, not only in solvents that are miscible in water, but also in terms of processes where hydrophobic surface area decreases, like protein folding. There's a interesting effect that happens if you measure the thermodynamics of this process. If you take, and maybe this is easier to illustrate if we just think about taking a beaker of some kind of non-polar stuff, maybe it's benzene, and benzene isn't colorful, but we'll just color it yellow, orange to make us think of oil and butter and stuff. And then we'll have here blue for water. And we're going to think about what has to happen, or what the thermodynamics of the process are, to take a single molecule of benzene and dissolve it in water. And you can do this. It's benzene isn't miscible with water very well, but you could get a little bit of benzene in. So we're going to take it here and put it in here. And we're going to measure the change in thermodynamic parameters when we transfer benzene from being in its own solution to being in water. Okay? So we sort of have, I'm sorry, I want to draw a before picture and an after picture. I know that's annoying, and I'm sorry. Before, after. Sort of feels like Sesame Street with Grover and prepositions near and far. You probably don't know that, right? Sesame Street was a thing past your time. Did you? Okay. All right. I still watch it. All right. So before, you just have a simple benzene solution, benzene neat, and you have a simple water solution. And afterwards, you have, say, some benzene molecules dissolved in water, and then they're surrounded by this shell. So you've got benzene in aqueous solution. All right. So I'm trying to figure out how to explain this because it's complicated and I always get it wrong, and so I'm anxious to not get it wrong. If you measure the heat capacity of the simple solution of water, you remember heat capacity is the amount of energy the amount of heat you have to add to increase the temperature. And it has a technical definition as well. Heat capacity is the first derivative of enthalpy with respect to temperature at constant pressure. In other words, if you were to measure the enthalpy of this simple solution of water as a function of temperature, the slope is the heat capacity. All right? And you can measure, of course, the heat capacity for a simple solution of water, and you can measure it after when you add benzene. And when you add benzene, the heat capacity increases. Meaning that if you were to take the enthalpy of this benzene in aqueous solution and go versus temperature, the slope would be sharper, right? And when you measure heat capacity before and after a process, you can you can take Cp heat capacity after minus heat capacity before, and that gives you a change in heat capacity. Alternatively, you could take the overall change in enthalpy for this dissolving reaction and plot it versus temperature, and you would get, and the slope of that plot would give you delta Cp. All right? A couple of different ways to think about it. But in general, for dissolving benzene in water and for other processes where you increase nonpolar surface area, you have large positive values for delta Cp. And that turns out is a hallmark of processes that are driven by the hydrophobic effect. It can be difficult to rationalize this, so I did want to talk about it for just a little while. Why do you think the heat capacity would go up if you put a nonpolar molecule in solution? Go ahead.
I mean, you talked before about how it increases the strength of the hydrogen bonds.
Uh-huh.
So, temperature changes how fast the molecules can move, so they aren't going to want to move as much because that involves weakening those hydrogen bonds.
There's a ton of good stuff there that I'm afraid I'm going to miss. So I want you to say that again.
So you increase the strength of the hydrogen bonds in the area around the benzene ring, and heat capacity is the amount of energy you need to put in to increase it in temperature. And so the hydrogen bonds are stronger, then it's going to need to put in more energy to break them or get them to be more flexible and mobile.
Okay.
Increasing temperature makes molecules move faster.
All right. So that's a key point, that temperature, we're going to think of temperature as average molecular kinetic energy. And that's wild to me that I can put my hand on something that's hot and it hurts me because the molecules are moving really fast. So how is the benzene solution different than water? Aren't there hydrogen bonds in water that you have to break if you were heating things up? Go ahead.
So are we saying that dissolving benzene in water increases the heat capacity of the water or the benzene?
The heat capacity of the... Well, it's the heat capacity of the water, because our before and after, the things that are changing is the water solution. If we added everything up, if we're only moving one molecule over, the simple benzene solution, I guess, cancels itself out. Yeah.
Would the outcome be similar if we dissolved some water in the benzene?
Would the outcome be similar for dissolving water in benzene? I don't know. It's a good question, and I don't have an answer for you. Fortunately, most biology takes place in water instead of benzene, so we're okay thinking about it from that direction. Right, so when you have the solution of a nonpolar molecule like benzene in water, you've got more interactions and more things that have to change before the average molecular kinetic energy can increase. It's like you've got this heat sink in the middle of your solution, and there's places for energy to go before the temperature increases. So yes, you have stronger H bonds, so some of the heat you apply goes to breaking stronger H bonds that line the cavity. And then if you're going to, the water molecules that are in the water molecules that line the cavity already are less mobile and have less degrees of freedom. And so to increase, you're going to have to apply energy to increase their freedom and mobility. And that's freedom and mobility you have to do in a solution of benzene that you don't have to do in regular water. In other words, in these cavities that surround the nonpolar molecules, you've just got extra places for energy to go until you can increase the temperature. It's kind of a microscopic phase change. Do you guys remember when you're boiling water, the temperature doesn't increase? Because all the energy you put in goes to the phase change, right? Similarly here, the heat capacity is higher because it's almost like you have a microscopic or nanoscale phase, different phase of water surrounding the benzene molecules. People have talked about it as an ice-like layer. That's not precisely correct because it turns out ice actually has a lower heat capacity than water. So it's kind of complicated, but it is like you've got a phase change going on here. There's a sink for the energy to go into before you can increase the temperature. So why do we care? It turns out if you're studying proteins and you want to know what's the major driving force for protein folding, you can measure protein folding thermodynamics, and in general, protein folding has what kind of delta CP? Should it be positive or negative? Negative, right? Because we've talked about a large positive heat capacity coming when you expose nonpolar surface area to water. When the change involves hiding nonpolar surface area from water, then it's negative. So protein folding generally has a negative heat capacity, and in a lot of cases, the magnitude of that change in heat capacity is proportional to the change in exposed nonpolar surface area. Because the more nonpolar surface area you expose to water, the more ice-like layer you have to deal with. Okay, so as you're thinking about protein folding at some point in the future, you may hear people talk about, oh, well, this is clearly a hydrophobic-driven process because it has a negative delta CP, meaning that there's not burial of nonpolar surface when the protein folds. That's sort of where all of this is coming from. Go ahead, Kim.
Do we consider the hydrophobic effect a non-covalent interaction, or do we treat it as its own?
Do we consider it a non-covalent interaction, or do we think about it on its own thing? That's a good question, and I confess as a grad student, I didn't really understand the hydrophobic effect, and I thought it was all about greasy things like to stick to each other because the van der Waals interactions are so strong. And it is true that van der Waals interactions can be strong in the aggregate and with gazillions and gazillions of them. Otherwise, geckos can't crawl up walls, right? But relative to hydrogen bonds, the van der Waals interactions are weak, right? So it can't be driven by van der Waals interactions because the van der Waals interactions between your nonpolar molecules are not enough to pay for the hydrogen bonds that you lost. So it is a non-covalent interaction. I suppose you can think about it that way, but it's entropy driven rather than enthalpy driven, and it's complicated. It's only a thing in water, right? Yeah, go ahead.
And similarly, would benzene be more soluble in water than, for example, octane because it has the quadrupole moment?
Would benzene be more soluble in water than octane because of the quadrupole moment?
And
I
it
think.
has electron-rich polar
I think probably. Probably it's interactions between water and the benzene quadrupole that account for the fact that benzene and water will distill in an azeotrope. So any of you in organic labs that are trying to get rid of water, sometimes you'll use benzene as a solvent, and you can rotovap off the benzene and the water will be removed after a couple of times. We call it azeotroping water off, but yeah, it's another hand, Jared.
Yeah, so just about the entropy thing. So, like, when proteins fold the hydrophobic, let's go to the center, so they're
Uh-huh.
not exposed to the water, and like I understand that in terms of like dissolves life and all that stuff. But wouldn't the entropy increase more if you were taking away the surfaces that are actually binding the water? Because the hydrogen bonds in polar parts of the protein would be the ones that bind to the water.
Right.
So they're trapping the water, but the hydrophobic surfaces, they wouldn't really interact at all. So they'd dump the water.
Right. The nonpolar surfaces don't necessarily interact that well with water when they're exposed, but that forces the water molecules surrounding them. They don't have anything to interact with on the nonpolar face of the molecule, so they have to interact tighter with each other, and their entropy decreases. Whereas the polar side chains tend to be on the protein surface, but they can interact with water and each other before and after folding, and that doesn't make a huge difference.
So it's not that the water wants to necessarily not be interacting with the protein and be free somewhere else. It's just that it has more options where it can be more.
That's right. It's when the protein folds, you have water molecules whose freedom was restricted, but now they're free to do other things. Yeah. But we even find in my lab that there's evidence that if you can replace water molecules interacting with polar things on a protein surface with, say, the PEG polymer as an example, that's a favorable thing too. So I think it is fairly reasonable to think that any decrease in surface area would make a protein more stable because you're going to release more molecules of water. At least that's my sort of hand waving. I didn't wave my hands. Now I did. Okay, good. What else? There was something I was going to say that I lost, so maybe it's not important. Oh, people have talked about how can protein folding be entropy driven. The process for protein folding generally has a favorable free energy. As to whether, when the protein folds, what delta H and delta S are can be complicated. And in general, for protein folding, the change in heat capacity is negative. But some people ask, so when the protein folds, you go from a conformation that was quite flexible to one that has a lot of less freedom. So how could this possibly be driven by the hydrophobic effect? And the answer is just that the impact of releasing all of these water molecules to bulk solvent just pays for the restriction in freedom that you have, plus all the new interactions you gain in the folded protein that you didn't have before. Let's see. Oh, I know what I was going to say. It turns out the hydrophobic effect is so important that some people have modeled protein folding as being exclusively about the hydrophobic effect. So Professor Ken Dill did some really important work early on with a two-dimensional lattice model of protein folding where, and this is great because we have a grid here, so we can totally do this. So the open circles are polar amino acids, and the filled circles are non-polar amino acids. And he set up a system computationally where if you had non-polar amino acids next to each other, that would be -1 in energy. If you had polar amino acids next to each other, that would be 0. And if you had a polar amino acid next to a non-polar amino acid, that would be 0. So no favorable polar interactions, just ignoring those completely. And the question was, can you specify specific shapes based on that assumption alone? So I think Dill started with a really, really simple molecule. Dang it, I'm going to have to draw smaller circles. So let's just imagine a polymer like this, and let's put the two non-polar residues on the end. Okay? And this polymer can change its shape, but the distance between any two circles that are attached to each other can only be 1 unit in our square, right? So I could put this one here or this one there. So let's just start to draw various potential conformational states. And can you think of other options? I mean, we could just draw forever. What are the energies of these 3 ones that I've drawn, just based on what I've told you there? They're all 0 because there's no conformation where the nonpolar groups are close to each other. But based on this sequence, there is one and only one conformation that gives you energy equals -1. And he was able to do this with much more complicated sequences and demonstrate that the ordering of polar and nonpolar residues is frequently enough to specify a full three-dimensional shape. And if you go look at the coil literature for protein folding, you can specify a structure where two helices pack against each other with a simple sequence that's hydrophobic, polar, polar, hydrophobic, polar, 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 repeating. And in general, that's all you need to know. So the hydrophobic effect is a big, important part of protein folding, and it's one that you shouldn't forget about. All right, we're done with chapter 3. We're going to skip chapter 4 because it's interesting, but a lot of geozoology. We're going to go to chapter 5 and only spend a little bit of time there because that's acid-base, and you should know that already. We're going to do some stereochemistry, and then we'll get into reactions. So I will see you next time.